Hi boys and girls. In the last class I told you about the binary numbers, then the tools we use, etc. Today we see the binary arithmetic. So what we see in this session is that you will learn the learning outcomes from, you will understand the learning outcomes from this session. Then you will know about binary addition with and without carry, and binary subtraction with and without borrow. The three representation of negative numbers or numbers in general, the sign, magnitude, the ones complement and twos complement representation, and their arithmetic, and finally we will see the summary. What you will learn in this session are you will learn the binary arithmetic, then you will learn the representation of positive and negative numbers with the ones complement, twos complement, and sign, magnitude representation. Then you will learn the subtraction with the ones and twos complement methods. So if you look into binary addition, all the numbers are from 0 to 0, 0, or 0 to 1 only 0 and 1 is present. So all numbers are limited to 0 and 1. So when a 0 is added with 0, it gives a 0. When a 0 is added with 1, it gives a 1. 1 plus 0 is a 1. And 1 plus 1 is actually a 2 in decimal, which is nothing but 1 0. That is a 0 with a carry 1. This is actually 1 0, number 2. Okay, there cannot be a number 2, it is just 0 with a carry 1. There's a carry in addition. So if you add a larger number, it may look like this. So this carry should be accounted for. So if you look here, it is a 1 plus 1, which is 0 with carry 1. So this carry comes here. Okay, that is added with this. So it's a 1 plus 0 plus 1, which is a 1 plus 1. It's again a 0 with the carry 1. So that carry comes here. Okay, I hope you can see this. So again 1 plus 1 is a 1 0 with the carry 1. So here it is a 1 plus 1 plus 1. So that is a 1 plus 1 is a 1 0 plus 1 is a 1 1. That is a with a 1 with the carry 1. So that carry comes here. That carry when added with 1, it gives 1 0. 1 0 with there's a carry here. 1 plus 1 is 1 0. Then I have carry comes here. 1 plus 1 is 1 0 plus 1, that is a 1 1. That is 1 with carry 1. So that comes here. Again it is a 1 1 with carry 1. Okay, that carry is added here. That becomes a 1 plus 0 plus 0 is a 1. Hope you understand this. You write many such numbers, add them, and understand the binary addition. This is how the carry propagates from left to right. And when it comes to binary subtraction, 0 minus 0 is a 0. It is clear. 0 minus 1, 0 is greater than, 0 is less than 1. I'm sorry, 0 is less than 1. So 0 minus 1 is a 1. Because 1 plus 1 is 1 0. It's a 1 with a borrow 1, because this side has to borrow a 1 from elsewhere and make it a 1 0. Minus 1, that is a 1 with a borrow 1. And 1 minus 0 is a 1, and 1 minus 1 is a 0. So this is how the binary subtraction happens at a bit level. If you look at the binary subtraction for larger numbers, if you say this is a 1 1 0 1 0 1 minus 0 1 1 0 1 1, that is a 1 minus 1 is a 0. There is nothing to worry about. And there is a 0 minus 1. 0 is less than 1, so 1 should be borrowed from here. That is indicated by this 1 here. Okay, it's a 1 0 minus 1, it becomes a 1. So here it becomes a, when this 1 is taken to the right, this becomes a 0. 0 minus 0 is a 0. Again here comes a 0 minus 1. Again it's a 1 with a borrow 1. So that this point becomes a 0. It becomes a 0 minus 1. So that this 1 is taken from here as a borrow. So that becomes a 1 0 minus 1 is a 1. So this is a 1 1 0 1 0. You can add these things and verify this. Add this number with this number to get this number. So that is how binary subtraction. There are digital circuits for doing this binary addition and binary subtraction. We will come to all that. And one problem in binary circuits is that all these numbers are represented by zeros and ones. So then how can we represent negative numbers? Because negative number usually we denote by a minus sign, which cannot easily be represented as in binary arithmetic. So we have to represent by a 0 or a 1. That negative sign also has to be represented by a 0 or 1. So how do we represent negative numbers? That becomes a question. So there are three ways in which we put it, either as a sign magnitude representation, or as ones complement method, or as twos complement method. Let us look about an unsigned number. Unsigned number is always is used to represent positive numbers alone. An n-bit representation, suppose there is a 3-bit number, it can represent from 0 to 7, like 0 to 2 raised to n-bit representation can any number from 0 to n minus 1. If it's a 3-bit number, it is from 2 raised to, it is 2 raised to n minus 1. Okay, this 2 cube 8 minus 1, it is not 2 raised to n minus 1, it is 0 to 2 raised to n minus 1. I will correct when I put this presentation. So 3-bit number means it can be from 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So 0, 0, 0, 2, with the 3 bits you can represent from 0, 0, 0 to 1, 1, 1. So what is that? 0 to 7. That is 0 is to 2 raised to 3 minus 1. That is 2 cube is 8 minus 1, 0 to 7. If it is a 4-bit number, I can represent from 0, 0, 0, 0 to 1, 1, 1, 1. What is that? 0, 0, 0 is a 0 and 1, 1, 1, 1 is 15. So that is 0 to 15. That is 2 raised to 4 minus 1. That is 2 raised to 4 is 16. Minus 1, that is 15. Numbers from 0 to 15 can be represented with a 4-bit representation. That is a case of an unsigned number. Signed numbers are able to represent both positive and negative numbers. So these unsigned numbers are used to represent only positive numbers, but signed numbers are used to represent both positive and negative numbers. So what happens is the leftmost bit, I told you, that is the most significant bit. The rightmost bit is the least significant bit. Why I call it the least significant bit? Even if that bit is flipped, if a 0 becomes a 1 or a 1 becomes a 0, there is very minimal change in the value of the number. But that is not the case with the leftmost number. That is the most significant bit. If that 1 becomes a 0, there is a great change in the value. So that is called the most significant bit. So what happens in the sign magnitude representation is this MSB is used to represent the sign. If that is a 1, it is treated as a negative value. If it is a 0, it is treated as a positive value. That the most significant bit is used as a sign bit, which represents whether the number is positive or negative. If the sign bit is a 0, the number is positive. If the bit is a 1, the number is negative. That's the usual practice. So there are 3 ways in which you can represent negative numbers. One is a sign magnitude representation, just I told you, and there is a 1's complement method and the 2's complement method. So when I look at the sign magnitude representation, if the MSB is a 1, the number is negative. Like if I have 1, 1, 1, 1, so this can represent up to 7 only. Okay, a 4-bit representation means the number, there is sign bit MSB, then the remaining bits only. So if it is a 4-bit number, it can represent all values from minus 7 to 7. Okay, 1, 1, 1, 1 represent this 1, this is the one in blue color that represents the sign bit. It is a 1, meaning that's a negative sign. So it's a minus value. Minus 1, 1, 1 represents a 7. So it is a minus 7. And 0, 1, 1, 1 represents a plus 7. Okay. I have a 1, 0, 0, 1 means it's a minus 1. It's a 0, 0, 0, 1, it's a plus 1. So if the MSB is a 1, it's a negative value. If the MSB is a 0, it's a positive value. So one drawback here is in this sign magnitude representation is that how can we represent a 0? You can either put it as 0, 0, 0, 0. Okay, so 0 indicating that is a positive sign, and the 3 zeros indicate that it is 0. And as well as 1, 0, 0, because it doesn't have a sign. So you can represent it as 0, 0, 0, 0 or as 1, 0, 0. There is a duplication in the code for 0. So this means that we are using the available codes inefficiently. Okay. So again, when this number is used in the digital circuitry, arithmetic circuitry, all these things are done by digital circuitry. So then that circuitry has to account for 2 codes representing the same number. That causes additional complexities. Then the range of the number is it is 2 raised to n minus 1 minus 1 to 2 raised to n minus 1 minus 1. Like it is this is a 4-bit representation. 1 bit is set for sign. So then there are only n minus 1 bits. Okay. So this can represent from 2 raised to minus 2 raised to 4 minus 1. 3 minus 1 is 2 cube is 8. Minus 1, that is minus 7 to plus 7. This can represent this 4-bit representation can represent values from minus 7 to 7. But there is a duplication in the code for 0. That is an inefficient use of the available code. So that should be corrected someday. So that is a problem with the sign magnitude representation. There is a positive 0 as well as a negative 0. So some care should be taken in the circuitry. Again, inefficient use of the available codes, that is a problem. And the range is from minus 2 raised to n minus 1 minus 1 to 2 raised to n minus 1 minus 1. So what is this? This is from for 3-bit, for 4-bit it is minus 7 to 7, for 5-bit it is minus 15 to 15. Then there is another representation, that is a sign magnitude, sign magnitude representation. Again, there is another problem with the sign magnitude representation that causes errors in the adder circuits. All these things are represented as circuits. All these things are done by adder circuits. So suppose I have to add a negative number and a positive number, say like a minus 5 and 4. What it adds is 5 and 4 and adds a minus sign, making it a minus 9 rather than minus 1. So when I add minus 5 to 4, I should be getting minus 1. So what the circuitry will do with the sign magnitude representation is, it will take the first 3 bits, that is 5 and 4, 3 bits respectively of 5 and 4. So it doesn't take into account the sign. Then it adds these numbers and adds a minus sign. So instead of getting a minus 1, you may get a minus 9. So that means for adding those things, I have to make a dedicated circuit. That is, it has to account for the sign and all that. That becomes a little complicated. So to overcome these difficulties, people use a sign magnitude, one's complement representation. So complement means complement of a 0 is a 1, complement of a 1 is a 0. Like if the bits are flipped, it becomes a complement. So the negative number is obtained by taking its positive equivalent and flipping all the 1s to 0s and 0s to 1s. Okay. This flipping of 1 to 0 and 0 to 1, this is called complementing. Okay. A complement of 0 is a 1, a complement of a 1 is a 0. So minus 7 is represented as, this first one is a minus sign, that is represented as a 1. Why? Because it is a sign. Okay, it is a sign. And this 7 is actually 1, 1, 1, but in 1's complement representation, it is flipped. It becomes a 0, 0, 0. So minus 7 in 1's complement code, it is represented as a 1, 0, 0, 0. Okay. What about plus 7? Plus 7 means it is a positive number, so the first value should be a 0. Okay. Since it is a positive number, it doesn't have to be complemented. So what happens is 7 is written as 0, 1, 1, 1. Okay. This should be thoroughly understood. Minus 7 means first one you see is a minus sign, so the first MSB should be a 1. Since it is a negative value, the value should be complemented. So instead of writing 1, 0, 0, 0, you 1, 1, 1, 1, you write 1, then the complement of 7. 1 meaning the sign, and complement of 7 is 1, 1, 1, the complement is 0, 0, 0. So that value is 1, 0, 0, 0. Now, how do you write positive 7? Positive 7 means the MSB is a 0. So, the MSB is a 0. So, you write 0. Then it's a positive number. So, I don't have to complement that. So, that I simply write 0, 1, 1, 1. So, this solves my problem with the addition of negative and positive numbers, because when I say minus 7 plus 4, that is equivalent to minus 7 is 1, 0, 0, 0 plus 0, 1, 0, 0. This is 4. Why is it 0, 1, 0, 0? Because it is a positive number, so the MSB is a 0, and the remaining part is a uncomplemented form, because it's a positive number. 1, 0, 0 plus 0, 1, 0, 0. What you get is a 1, 1, 0, 0. Now 1, 1, 0, 0 is nothing but it doesn't have a carry in addition. So 1, 1, 0, 0 is, if you complement it, you can see that the first value is a 1. So this MSB is a 1. So this MSB is a 1, meaning that it's a negative number, so it should, one's complement should be taken. So this 1, 0, 0, when complemented, it gives you 0, 1, 1. So it is 1, 1, 0, 0. It is nothing but the 1's complement for my minus 3. Okay, 1's complement of minus 3. Okay, so minus 7 plus 4, you get as minus 3 by simply adding this. In the earlier case, in the sign magnitude representation, what happens is sign is treated separately. So when minus 5 and 4 are added, what it actually adds is 5 and 4 and adds a negative sign, reaching in a wrong result. Now if you take another example, 7 minus 4, that becomes a, now in this case there is no carry. I'll come back to this ones complement arithmetic later, but I will say this here also. If I say 7 minus 4, that is this 7 is 0 1 1 1, because 7 is a positive number, and you should start with a 0, and the remaining thing is the value of 7 uncomplemented form, that is 0 1 1 1. And what is 4? The first it is minus 4, so what I have to add is first is a 1, then 4 is represented by 1 0 0. Now I have to complement it, it becomes a 0 1 1. So that when I add, you get one carry here. There's a carry here. You get 1 0 0 0 1 0. Now if there is a carry here, now you can see that this is a 0 and it's a positive number, but that is not alone. There is a dropped carry here. That dropped carry should be added with this number, so that it becomes 0 0 1 0 0 0 1 1 0 0 1 1 is nothing but 3. 0 0 1 1 is 3, not minus 3, it is 3. Now here also the same problem comes, because 0 is represented by both 0 0 0 0 and 1 0 0 0, making the range of numbers from 2 raised to minus 2 raised to n minus 1 to n minus. Don't confuse, don't get worried by these equations. It is just a minus 7 to 7 for a 4-bit code. It is for a 5-bit code, it is minus 15 to 15. Okay. So here this problem in the wrong result in the addition of negative and positive numbers, that is circumvented, but duplicate 0 is not circumvented. Okay, duplicate 0 is still there. There are code for 0 0 0 0 and 1 0 0 0, meaning that there is a positive 0 as well as a negative 0. So that is an inefficient use of the available code. So this duplication of 0 can be circumvented by the 2's complement. So 2's complement is basically nothing but 1's complement plus 1. Okay, you take the 1's complement of a number. What is a 1's complement? When you see that it's a negative number, you add a 1 to the MSB and flip the remaining bits. Flip the bits of the number. Like if it is a minus 7, it should be 1 0 0 0. Why? First 1, because it is a sign. Then what is that 0 0 0 corresponding to? That is the complement of 1 1 1 1. Now you get 1 0 0. You have to add a 1 to that, it becomes a 2's complement. So minus 7 is represented by 1 0 0 1, and 7 is represented by 0 1 1 1. So 0 is equivalent to 0 0 0 1. 1 is equivalent to 0 0 0 1. Minus 1 is equivalent to 1, because it is a negative number. Then the remaining part is 0 0 0. It becomes a 1 1 1. Okay. Now the point is there is no duplicate 0. Okay, 2 is equivalent to 0 0 1 0. Okay, minus 2 is equivalent to 1 1 1 0. Minus 8 is represented as 1 0 0, because there is no duplication in 0, so that means the range of numbers are minus 2 raised to n minus 1 to 2 raised to n minus 1. So I can have a minus 2 cube, minus 8 to plus 7. Okay, minus 8 is represented as 1 0 0 0. Now if you look at the 1's complement subtraction, what I told you already, but I will say this once again. 7 minus 4 is nothing but 7 is a positive 1, so it is a 0 1 1 1, because this is a sign bit is a 0 and this one is a positive, so it is 1 1 1. Then plus 4 is a 1's complement form, that is first bit is a 1, then the remaining thing is 1 0 0, that should be complemented, so it becomes a 0 1 1. Now when I add, I get 0 0 1 0 with a carry 1, so this carry should be added with this, so making it a 3. So the result is a 3. This is a 0, so it is a plus 3. Now 4 minus 7 is nothing but 0 1 0 0, that is 4. This is a negative number, so this is plus, here it is a 1, meaning that is a negative sign. Then 7 is 1 1 1, which is complemented, so it becomes a 0 0 0. This is 1 1 1 1 1 0 0 with a carry 0. There is nothing to add. Now this number is a 1, meaning that's a negative number, so I have to take the complement of the remaining part. It becomes a 0 1 1, which is minus 3. This is, I say, 1100, which minus 3 means 110 in the 1's complement form. Now when I look at the 2's complement subtraction, what happens is 7 minus 4, if I say 7 is 0, 1, 1 because it's a positive number, minus 4 should be taken in the 2's complement manner. What is the 2's complement of 4? How do I take the 2's complement of minus 4? First bit should be a 1, okay. Then the remaining thing is a 1, 0, 0, that should be complemented, that becomes a 0, 1, 1. Add 1 to that, it becomes 1, 0, 0. It becomes 1, 0, 0, okay. Why I get 1, 1, 0, 0 here? First, why this 1? Because this number is a negative 1. Now what is the, I have to take the 1's complement of 4. 4 is equivalent to 1, 0, 0. 1's complement is 0, 1, 1. I have to add 1 to that to make it a 2's complement. So 0, 1, 1 when added with 1 gives you 1, 0, 0. So it becomes a 1, 1, 0, 0. When I added with, you get 0, 0, 1, 1 with the carry 1. This carry should be added with this carry need not be added. This is a 2's complement subtraction. This carry is ignored, which makes it a 3. Now 4 minus 7 is 4 is 0, 1, 0, 0. It's a positive number. Minus 7 becomes a minus means I have a 1 here. Then 7 is 1, 1, 1. That should be complemented. That gives me 0, 0, 0. 1 should be added with that. It becomes a 0, 0, 1. Okay. So what happens is 1, you get 1, 1, 0, 0, 1 with the carry. Forget about the carry. You don't have to worry about the carry. So this first number is a 1, meaning that is a negative number with 1, 0, 1. So this is a 2's complement representation. So what is this? You subtract 1 from this, it becomes a 1, 0, 0. If you take the complement of that, it becomes a 0, 1, 1, which is minus 3, which is correct. So you have to do a couple of numbers like this and understand this. So what you understood in this, you understood the binary arithmetic, then you understood the representation of positive and negative numbers with the help of sign magnitude representation, the 1's complement and the 2's complement. Then you learn the 1's and 2's complement arithmetic. With that we come to the end of the second session. I thank you all.